Welcome back, folks. We are continuing our work in section 5.1, differential equations. Today's lesson, we're talking about slope fields. Quick intro here, or quick side note. You might be wondering, why on earth is everything that we do in differential equations called section 5.1? The reason for that is because in our textbook, the only part of chapter 5 that is covered on the AP Calculus AB exam is stuff in section 5.1. I've chosen to split it up into several different lessons, which is why I'm calling them 5.1 intro, 5.1 slope fields, etc. Okay, before we jump into this new topic of slope fields, I would like to look at a couple warm-up problems. So I need you to get out your own blank paper. Hope that isn't too much to ask. So let's go ahead and take a look at this one. It says, find the general solution of the differential equation y prime equals x times y squared. Let's go ahead and start this process. The first thing I want to do is look at this, and I notice that there's no domain restrictions there. The reason why is there's nothing there that causes an undefined operation. Okay, so that's where we start the work. And don't forget that we have a 4-step process. Step 1 is to write the differential equation. Step 2 is to separate variables. Step 3 is to integrate. So let's go ahead and anti-differentiate both sides of that. On the left-hand side, we're going to get, using the power rule for antiderivatives, -1 times y to the negative first power. And on the right-hand side, we're going to get our friend x squared over 2 plus some constant. All right, let's go ahead and rewrite the left-hand side, make it look a little prettier. Now we need to rewrite this thing in the form of y equals. So I'm going to go ahead and make sure we note that our 4th step in this process is to rewrite this. To rewrite this in the form of y equals some function of x, I'm going to take the reciprocal of both sides. I'm going to divide both sides by -1 so that -1 moves to the right-hand side. There, we're done. And I would share with you that this is a correct answer, but it's not pretty. We've got fractions inside of fractions, and that really, I think we can do better than that. So let's go ahead on over here and take a look at rewriting that again. This denominator might be a little bit confusing for some of you, so let's explain where that came from. Okay, so let's take a look at what's going on in the denominator down here. I have x squared over 2 plus some constant. Well, I can write that constant as 2 times c over 2. And that gives me x squared plus some new constant over 2. It's not fair to use c, the same c in both of these. So what I should really do is go back and refer to this as the first constant. And now I have this new one that's I'm just going to call c. So I can leave the c that I have up here as c. All right, so this is certainly an improvement over what we had before, but it's still not pretty. So let's go ahead and rewrite that one more time. We have -1 divided by that quantity, so that's really just the reciprocal of that quantity with a negative sign out in front. And there you have it, folks. That is beautiful. Okay, let's take a look at another problem. Next problem we'll take a look at here is a bit tougher than the previous one. Find the particular solution. Okay, so now we're going to need to find the solution through a specific point of y prime equals x over y. The first thing I want to note here, y cannot equal 0. That is a domain restriction in our differential equation. Therefore, we have to include that in our particular solution. All right, let's go ahead and get started. I'm going to go ahead and write the differential equation. I'm going to separate variables. I'm going to integrate, and I get y squared over 2 plus, seriously, Bass. equals x squared over 2 plus some constant. From here, let's just multiply everything out by 2. That gives us y squared equals x squared plus some constant. It's different than the previous one, so I'm going to tag the previous one with a subscript of 1. Let's go ahead and solve for y now by extracting a square root. You know that when we extract a square root, we better put that plus or minus sign out in front of the square root symbol. This is our general solution. Notice that it's not written in the form y equals a function of x because I have both the plus and minus sign out in front of the square root symbol, so that is not a function. But we're ready to look and see if we can find the particular solution. And we're going to do that by subbing in 2 comma negative 3. So we have this, y equals plus or minus square root of x squared plus c. Well, I have to make a choice. Should I choose the positive square root or the negative square root? Fairly obvious. We have a y value here that's less than 0. So what we're going to do is choose the negative square root. So we sub in our value of negative 3. We got 2, we got a square, and we got to add c. Let's go ahead and take a look at this. This quantity right here, 4 plus c, we need that to equal 9. Because the square root of 9 is 3, we already have the negative sign taken care of here. That means that c equals. So we're ready to write our particular solution. Y equals the opposite of the square root of x squared plus 5. Now, I've made this big point to say we should always, especially when talking about our particular solutions, state a domain. I know that y cannot equal 0 from the differential equation, but we have this quantity x squared plus 5 under the square root symbol. That'll never equal 0. So this particular solution is defined for all x. Okay, folks, let's go ahead and take a look at another warm-up. Folks, this one is even tougher than the previous problem. It says find the particular solution of y prime equals 2 divided by the square root of 9 through the point 0 comma 9. If this one looks familiar to you, then you've been paying attention because this was question number 6 from the differential equation discovery that I had you do previous to this lesson. So let's go ahead and work through the complete particular solution of this differential equation. I'm going to start by noting this. We got y prime equals 2 divided by the square root of y. So automatically I'm thinking about domain restrictions here. Y not just greater than or equal to 0. I know it's under the square root, so you're allowed to take the square root of 0, but it's in a denominator. So we have to exclude 0 from that. So whatever we come up with as our final answer, we have to make sure that y is going to be greater than 0 with that solution. We're going through the point 0 comma 9. This is a y value greater than 0, so we're okay there. Let's go ahead and do our 4-step process here of write, separate, integrate, and rewrite. At this point, I'm going to try to solve for y. First thing I'm going to do is multiply both sides of this equation by 3/2. And that's going to give me y to the 3/2 power. So I've eliminated that coefficient out in front. 2x times 3/2 is 3x. C times 3/2 is some other constant. So I better go back and tag this as c sub 1. Next thing we're going to do is to solve for y, we're going to raise both sides of this equation to the 2/3 power. That's going to give us y equals the quantity 3x plus c to the 2/3 power. And this is our general solution. We need to find the particular solution, so we're going to go ahead and we're going to sub in the point 0 comma 9. Okay, so we have 9 has to equal the quantity. Basically, we got 3 times 0, which is 0, so we have just c to the 2/3 power. And I know some of you are like, oh, I'm going to get out my calculator and I'm going to raise both sides to the 3/2 power. That's just not necessary. I think you should be able to think through this one logically. Okay, we need that expression to equal 9. So let's just take a look at some multiples of 3 and see if we can't figure this out from there. If we take 27, raise it to the 1/3 power, that's the cube root of 27, which is 3. If we take 3 and we square it, you get 9. So that means this constant is 27. Now, I just thought through that one with a little bit of number sense. Of course, you can take both sides and raise it to the 3/2 power. If you take 9 and raise it to the 3/2 power, that's basically saying you're going to take the square root of 9 and cube it, and you get the same value. Okay, enough about that. Let's go ahead and take a look at this particular solution. So our particular solution is y equals the quantity 3x plus 27 to the 2/3 power. And if only it was that simple. I now want to talk about the fact that we have y cannot equal 0. There is a way that we could get y to equal 0. If we set 3x plus 27 equal to 0, then this entire expression will equal 0. That means we have x equals -9. But I said that y cannot equal 0. So I need to make sure I state it as this. X cannot equal -9. Okay, so what does that do for us in this problem? Remember this. Since y cannot equal 0, x cannot equal -9. We just showed that algebraically. So what do we have to do in the context of solving a differential equation? Okay, if you recall from our previous discussion of differential equations, we said for a particular solution, the domain, you have to pick a single open interval that contains the initial condition. Let's go back and look at the original initial condition. We had x equals 0. We had y equals 9. So I need to pick an open interval that includes x equals 0, but x cannot equal -9. So that means my domain must be for x greater than -9. And that is the final answer for this problem. Folks, that was terrible. That's a little better. So we have our final particular solution is y equals the quantity 3x plus 27 to the 2/3 power for x is greater than -9. And I want to just quickly talk about what the graph of this would look like. So I'm going to scroll up here a little bit and we're going to sketch this graph. Okay, so we know that this is a quantity raised to the 2/3 power. And if you remember from our previous conversations of any function that includes an x to the 2/3 power, we have a graph that kind of gives us that seagull shape. We have a cusp. And this one, that cusp is going to be at x equals -9. We've already said that we're only going to include the domain here where x is greater than -9. So it's only the right-hand side of that graph. I want to show you another reason why it cannot be the left-hand side of the graph, and I want to think about it in terms of derivatives. If we think about the derivatives here, everything from here over is increasing, so its derivative has to be positive, and everything from here, from x equals -9 to the left, is decreasing, so its derivative has to be negative. Let's go back and look at the original differential equation. We have y prime equals 2 divided by the square root of y. Taking another look at that, I'm going to tell you this, y prime has to be greater than 0 because we're taking the positive constant of 2, we're dividing it by a square root, which has to also be, in this case, greater than 0. So that quantity will be positive. Therefore, the only part of this graph that's relevant is this part where we're increasing. All right, folks, one last thing I want to talk about here, and that's what the graph of this looked like in the differential equation discovery activity. This is what that graph looked like in that activity. And again, as we already talked about, we only see the part of this graph that's greater than -9. But what about all those little lines on the graph? It certainly looks to me like this graph kind of almost follows the path that's put on the screen by those little lines. And I'll tell you this, all of those lines, so all those lines on this graph are what we call a slope field. And that is the subject of this next lesson.